Good morning, everyone. My name is G. Vishnumurthy, working as a lecturer in Government Degree College for Women Vanaparthi. Today, my topic is semiconductors and junction diodes. And before class, we will see about the band theory. Depending upon the band theory, the materials are classified into three types. One is the insulators, second one is semiconductors, and third one is conductors. Before we going to semiconductors and p-n junction diode, what is an atom? In 1915, the Niels Bohr was introducing a atomic model. That model is known as the Bohr atomic model of an atom. Here you see this is the structure of atom. In this, the center point is called as the nucleus of the atom, and the nucleus consisting of two elements. Those are known as the protons as and neutrons. The protons having the positive charge and the neutrons having the no charge, that is neutral in charging, and the electrons are revolving around the nucleus within the stationary orbits. That stationary orbits are denoted by k, l, m, n, so and so. So these stationary orbits are having the electrons, and we know that the probability to finding the electron in a stationary orbit is known as the orbital. So those orbitals are again divided into s orbital, p orbital, d orbital, g orbital, so and so. So so these pink colors appeared in the atom are known as the electrons, and in blue color dots is known as the protons, and the black color dots in center is called as the neutron. So this is the about an atom. What is conductor? An element that can easily pass the current is known as a conductor. We can also say that an atom can easily lose an electron from its outermost shell, because of in outermost shell there is a lot of empty place is there, but the number of electrons present in the outermost shell will be less. That's why the distance between the electron to electron in outermost shell is very large. That's why they are bonding loosely bonding to each other. And we know that the conductors having a loosely bound electrons in their outer shell, these electrons require a small amount of energy to free them from conduction. So that due to the loose bonding in outermost shell, we will apply small amount of energy to the electrons which are present in the valency band. That electrons will free from the bound. Those free electrons causes the current conduction. The force on each electron is enough to free it from its orbit, and it can jump from atom to atom. The conductors can conduct. So conductors are having low resistance. We know that the resistance is inversely proportional to current conduction. When the resistance is high, then the current conduction is equals to low, and when the resistance is low, then the current conduction is high. You see this is about the conductor structure. In internal structure of the conductor, the figure shows. And next we are going to insulators. Insulators have tightly bound electrons in their outer shell. These electrons require a very large amount of energy to free them from conduction. The force on each electron is not enough to free it from its orbit, and the insulator does not conduct. Insulators are said to have a high resistance or high resistivity. In insulators, all electrons are closely bound together in outermost orbital. That's why more energy is required to free from the bonds. Sometimes those high energy spoil or destroy the outermost orbital like atom. So that's why the complete element will be destroyed. So due to the closely packing of electrons in outermost shell, there is no free electrons available in the valency band, so that the material could not conduct the current. So the type of materials are known as the insulators. And the second one is semiconductors. And now the definition, you see the definition of the semiconductors are those materials that have a resistance between that of conductors and insulators. Their electrons are not free to move, but a little energy will free them for conduction. The two most common semiconductors are known as the silicon and germanium. Here you see this, the semiconductors lies between the conductors, conductors to insulators, because of their energy gap between the valency band to conduction band is very less, to comparing the conductors and insulators. So that when we apply small amount of energy to the valence band electrons of semiconductors, those electrons will free from the valence band and to cross the energy gap and reach the conduction band. But when we apply the external energy, then it is possible. If we will not apply any external energy, all electrons are exist in the valency band after we will giving the external energy. And now you see the energy bands in conductors, insulators and semiconductors are there. You see this, this is about the insulators. In insulators the energy gap is very high between the valency band to conduction band. And here you see this energy band of conductors. There is no forbidden energy gap between the valency band to conduction band, so that the valency band is overlapping with the conduction band. That's why the electrons which are present in the valency band are freely moving from valency band to conduction band. But here you see the second figure shows the semiconductors energy bands. The energy gap between the valency band to conduction band is lies between the conductors to insulators. So energy gap of the difference between the energy levels of any two orbital shells. The band, another name of an orbital shell is known as a shell. The conduction band, the bond outside the valency band. So these are the three bands present in the atomic structure. And now you see the silicon atom and covalent bands. How covalent bands are formed in silicon? The silicon has a valency of 4, that is the 4 electrons in outer shell. Because of the atomic number of the silicon is 14, so 10 electrons are tightly fitting in lower bonds and 4 electrons are free in the valency band. That's why the valency electrons are known as the valency of the silicon. So each silicon atom shares its 4 outer electrons with 4 neighboring atoms. These shared electron bonds are showing as horizontal and vertical. Here you see this is the horizontal and this is the vertical bonds between the silicon. Those bonds are known as the covalent bands. Due to covalent bands, the silicon acting as a semiconductor. Here if you heating the silicon atom, some of the covalent bonds will be break up. That's why the electron and hole pairs are formed. Sorry, electrons and holes are formed in the atomic structure. So we have seen that in silicon it releases the electron from their bond. This creates the electron hole pairs which are then available for the conduction. If more heat is applied, the process continues. So more heat, more current, less resistance. The silicon is acting as a thermistor. Its resistance decreases with the temperature. This figure shows when we apply large amount of heat, then we got the high amount of electrons and hole pairs. So that causes the electrons and holes are causes the heavy amount of current pass through the material. Its resistance will be decreases because of there is no covalent bands, or the covalent bands between the silicon to silicon atoms will be decreases. That's why the resistance of the silicon will be decreases to increasing of the temperature. So when the resistance is decreases, then the current conduction of the material should be increases. Now we are going to formation of p type of material and n type of material of silicon. So intrinsic and extrinsic semiconductor. Now you see the definition of the intrinsic semiconductor. Semiconductor in its pure form is called as the intrinsic semiconductor. It is undoped. We know that the semiconductors are dividing into two types. One is the intrinsic semiconductor, and second one is the extrinsic semiconductors. The semiconductors are exist in the pure form is known as the intrinsic semiconductor. Then we will, and second type is when we add some impurity or like trivalent impurity or pentavalent impurity to the intrinsic semiconductor, then we got the extrinsic semiconductors. Okay, a semiconductors in its impure form, that is doping some impurity to the intrinsic semiconductor, as known as impure form, or the semiconductor which is doped is called as the extrinsic semiconductors. Now the doping of an intrinsic semiconductor definition, you see this, the doping is a process of adding impurity to a pure semiconductor is called the doping of a semiconductor. When semiconductor is doped, then we got the p type of material and n type of semiconductor material is formed. So n type of semiconductor material have the majority of electrons, and the p type of semiconductor material having the majority of hole. Now we will go to n type of material. For the n type of material, we will add pentavalent impurity to the intrinsic semiconductor like silicon and germanium. Here you see this the pentavalent element like phosphorus. So the atomic number of the phosphorus is 15 in and about of 15 electrons. The 10 electrons are closely or strongly filled in the lower orbital, and 5 electrons are filled in the valence band. Those 5 electrons are called as the valency of the phosphorus. So these 5 electrons are free in valence band, and those are loosely bound together. So this is the phosphorus atom. It consisting of the 5 electrons in outermost orbital. Now we will adding this phosphorus into silicon. Out of 5 valence electrons of phosphorus, 4 electrons are making a bonds to the outermost electrons of the silicon, and another electron is free from the phosphorus atom. So every phosphorus atom will give the one free electrons. That's why when we add some impurity like phosphorus material to the silicon, then we got the larger amount of electrons, free electrons. Those free electrons are causes the current conduction in the n type of material. And also in n type of material, the majority carriers are known as the electrons, and minority carriers are called as the holes. So this n type of semiconductor material, suppose we remove a silicon atom from the crystal lattice, then we replace it with a phosphorus atom. We now have an electron that is not bonded. It is thus free from conduction. Here you see this when we add only one phosphorus atom to the crystal lattice of the silicon, then we got the one free electron. When we add more phosphorus atoms, then we got the more free electrons at the crystal lattice of the silicon. Here you see this two phosphorus atoms are adding in the crystal lattice, then we got the two free electrons. So let's remove another silicon atom and replace it with as more as electrons are available for conduction, we have increased the conductivity of the material. Phosphorus is called as the dopant because of the impurity atom is known as the dopant. If we know, apply a potential difference across the silicon, and then we got here this side is positive side and this side is negative side. When we will add potential difference across the silicon, then we got the two faces, that is the positive face and negative faces. So these negatively charged electrons are moved towards the positive side, and the positively holes when the positively holes are minority carriers in n type of material, those are moving towards the negative side. So in this particular case, the motion of the free electron and motion of the hole will causes the current conduction. So this is about n type of material. And now n type silicon material, this type of silicon is called as the n type. This is because of majority charge carriers are negative electrons. A small number of minority charge carriers holes will exist due to the electron hole pairs being created in this silicon atom due to heat. The silicon it's still electrically neutral because of as the number of protons is equal to the number of electrons. Now we are going to p type of material, and when we got the p type of material, we will add impurity like trivalent impurities like boron, so on. So the atomic number of the boron is 5. Out of 5 electrons, the 2 electrons are closely or strongly bonded in the lower orbitals of the boron, and the remaining 3 electrons are free in the valency band. So the valency of the boron is called as the 3. These 3 electrons are making the bonds between the silicon to silicon atoms, silicon to boron atoms. But here you see, out of 5 electrons, 3 electrons are free in boron. These 3 electrons are making covalent bands with the free electrons of silicon. Here you see this is the silicon, and this is the pink color dot is showing the boron atom. This is the boron atom, this is the boron, and also this is the boron atom. So every boron atom consisting only 3 electrons, but the silicon having the 4 electrons. So the fourth electron is the fourth electron. So in this section, the fourth electron in the boron is empty. So that's the empty is known as the empty place is known as the boron. In boron atom is called as the hole. So every boron atom will give the one hole. So that when we add impurity to the silicon, then we got the number of holes in the silicon lattice. You see if you add one boron atom to the silicon lattice, then we got the one hole. So if you add more number of boron atoms to the crystal lattice of the silicon, then we got the more number of holes. So these holes are moving towards this side, and some of the minority electrons are moves towards the positive side. So the motion of the electron and the motion of the holes will causes the current conductivity in the p type of material. So this is about the p type of material. A current will flow, this time they carried by the positive holes. Note that the positive holes move towards the negative terminal, and here you see the hole and holes and hole current. The holes are moving toward this side, and the electrons are moving to this side. That's why the current conduction due to two reasons, that is the holes movement of holes and the movement of electrons. The p type silicon, this type of silicon is called as p type. This is because of the majority charge carriers are positive holes. A small number of minority charge carriers are called as electrons will exist due to electron hole pairs being created in the silicon atom due to heat. The silicon is still electrically neutral because the number of protons is equal to the number of electrons. Donor and acceptor impurities. Acceptor dopant, an acceptor is a dopant atom that when added a semiconductor can form a p-type region. The donor a donor is a dopant atom that when added to a semiconductor can form an n-type region. The pentavalent impurity, n-type material is formed, phosphorus is pentavalent impurity. Trivalent impurity, p-type of material is formed, boron is called as the trivalent impurity. Now we are going to p-n junction diode with another video.
This tutorial animation covers how a PN junction semiconductor works, what is forward bias and reverse bias, what is diffusion current and drift current, and what is avalanche breakdown. What is PN junction semiconductor? And how is it formed? It is a combination of p-type semiconductor with n-type semiconductor to achieve the practical utility of both. It's formed when a p-type semiconductor is joined to a n-type semiconductor. Now with the help of this animation, let's see how the p-type semiconductor and n-type semiconductors work. So the p-type semiconductor has holes which are positively charged, and the n-type semiconductors have electrons which are negatively charged. So you can see free holes which are positively charged are available in the p-type, and free electrons which are negatively charged are available in the n-type. So this is the region where the p-type and the n-type joins, or the junction which is formed, which is called as the p-n junction. So this is the p-n junction. What happens when a p-n junction is made? Electrons near the junction jump from n-type semiconductor towards the p-type semiconductor, and holes near the junction jump from the p-type semiconductor towards the n-type semiconductor. This phenomena creates a space charged region at the junction. So this is the space charged region which is created at the junction. Electrons are available in the p region at this space charged region, and holes are available in the n region at this space charged region. An electric field is also created in this space charged region because of the movement of these holes and the electrons, and the direction of the electric field is from the n-type region towards the p-type region. Some electrons move back from p to the n in this space charged region, and some holes move back from n to the p in this space charged region. So it moves back also, and this continues to happen till an equilibrium is reached at this region. This movement of electrons and holes in the space charged region gives rise to a current, and this current is called as diffusion current. Now let's see forward bias. In forward biasing, positive terminal of the battery is connected towards the P region of the PN junction, and the negative terminal of the battery is connected to the N region of this PN junction semiconductor. And you can see the positive terminal repels the holes in the p region, and the negative terminal repels the electrons towards the junction in the n region. So a pressure is acting towards the junction, and this result in the junction to shrink. You can see the junction is shrinking there. Due to this repulsion, the depletion region, or the space charged region, narrows down, as you can see in the animation. If the voltage in the forward bias is above a specified range, these electrons in the N region drifts through the junction and migrates to the P region, and the holes in the P region drifts through the junction and migrates towards the N region, as like this. You can see the electrons are drifting through the junction towards the P region, and the holes are drifting through the junction towards the N region. Now the current starts to flow across the circuit, and this current is called as the drift current. Now let's see reverse bias. For reverse bias to achieve in PN junction semiconductor, the negative terminal of the battery will be connected towards the P-type semiconductor, and the positive terminal of the battery will be connected towards the N-type semiconductor. So holes get attracted to the negative terminal of the battery. You can see the animation over there, and the electrons get attracted towards the positive terminal of the battery, as per the animation over there. So this result in the increase of the depletion region, the depletion layer, or the space charged region, because you can see the repulsion of the electrons and the holes is happening against the space charge or the depletion layer. So what happens is that this result in the increase of the depletion layer, as see in the animation. That's the depletion layer over there. Now the PN junction act as an insulator and will not allow any current to flow in the circuit. So this junction, or this depletion layer, now will be acting as an insulator and will not allow the flow of the electrons or holes in that region. But in a particular condition, if the battery voltage is above a particular limit, what happens is that this particular limit is called as reverse bias breakdown voltage. So if the battery achieves this reverse bias breakdown voltage, what happens is that electrons and the holes break down through the p-n junction and crosses this junction, resulting in the current to flow through the circuit. So you can see the electrons which are negatively charged crosses this junction, that is breaks through this junction and moves towards the p region, and the holes which are positively charged breaks through this junction and moves towards the n region, resulting in the flow of a current. This breakdown is called as avalanche breakdown. In this process, the current flowing through the p-n junction is very high, and ultimately the p-n junction gets damaged due to the overheating caused by this excess flow of current. This is how a p-n junction semiconductor actually works. So I believe you understand all the topics covered in this tutorial. Please click the subscribe button for getting more tutorial video updates. You can also visit our website techfreaksinfo.com or our YouTube channel youtube.com/techfreaksinfo for more tutorial video contents. Please like, comment, share to motivate our team because we need your support to keep going. Thanks for watching this video. Have a great day.
Hey friends, welcome to the YouTube channel All About Electronics. So in this video and the subsequent videos, we will learn about the diode. And these are the following topics that we will cover in the series of videos. And in this particular video, we will learn that what is diode and how the VI characteristic of the diode will look like. And we will also see the equivalent circuit for this diode. And in the subsequent videos, we will learn about the device physics of this diode, and we will also see the different applications of the diode. So now the question is, what is diode? Now we all know about the resistor. It is the most widely used type of passive circuit element, and it allows the flow of current in both directions. Similarly, this diode is a two-terminal semiconductor device which allows the flow of current only in a one direction. And if you see the symbol of the diode, then it looks like this. So here this arrow indicates the direction in which this diode allows the flow of current. Now the one terminal of this diode is known as the anode, and the second terminal of the diode is known as the cathode. Now whether this diode will allow the flow of current or not, it depends upon the polarity of the voltage that is applied between this anode and cathode. So if the voltage that is applied between this anode and cathode is positive, then in general we can say that this diode will allow the flow of current in one direction. While the voltage that is applied between this anode and cathode is negative, then it will not allow the flow of current. So now when this diode is connected in particular circuit, and if you want to analyze that circuit, then the circuit can be analyzed by knowing the voltage and current that is flowing through this diode, and that can be found using the VI characteristic of the diode. Now for the resistor, we know that it is a linear element and the relationship between the voltage and current is linear. So using the Ohm's law, we can easily find the voltage and current through this resistor. But unlike the case of resistor, the diode is a nonlinear element. So the relationship between the voltage and current for the diode is nonlinear. And moreover that this diode allows the flow of current only in a one direction, and it almost blocks the current in the reverse direction. Now if you look this graph, then it looks like the graph is symmetrical in both directions. But don't get confused by the symmetricity, because here in this graph both positive and the negative axis have a different scale. For example, on the positive y-axis we have a scale in milliampere, while on the negative y-axis we have a scale in microampere. Similarly, on the positive x-axis, if you see, the voltage varies like 0.5 volt, 1 volt and 1.5 volt, while if you observe on the negative x-axis, the voltage scale varies like minus 10 volt, minus 20 volt and minus 30 volt. So because of the different scale, this characteristic looks symmetrical on both axes. But if we keep the same scale on both axes, then the diode characteristic will look like this. So as you can see, in the reverse direction, the current that is flowing through the diode is almost negligible. So using this VI characteristic of the diode, we can easily find the voltage and current that is flowing through the diode. And using this, we can easily analyze any circuit which contains these diodes. But because of the nonlinear characteristic of this diode curve, it is a bit difficult to find the voltage and current very easily. So what we can do, we can approximate this diode characteristic, and using this we can analyze the circuits. So first of all, what we will do, we will consider this diode as an ideal diode, and for this ideal diode we will see the VI characteristic. and also we will see the equivalent circuit for this ideal diode. And step by step we will introduce few more parameters to this ideal diode, and using this we will approximate the diode characteristic curve. So for the ideal diode, whenever the voltage that is applied between the anode and cathode is positive, then simply it will act as a closed switch. On the other end, if the voltage that is applied between this anode and cathode is negative, in that case simply it will act as a open switch. So now let us see the VI characteristic for this ideal diode. So in the case 1, when the applied voltage is positive, on the VI characteristic we will get the vertical line. And for the case 2, when the applied voltage is negative, then for that case we will get the horizontal line on the negative x direction. So this is the VI characteristic for the ideal diode. So now whenever the positive voltage is applied to this diode, then it can be said that the diode has been forward biased and it will allow the flow of current. While on the other end, whenever the negative voltage is applied to this diode, then it will not allow the flow of current, and simply we can say that it has been reverse biased. So we will talk more about this forward and reverse bias at the later part of the video. So now let us take one simple example in which the diode is connected in series with the voltage source and the resistor. Now here we are assuming that the diode is an ideal diode. It means that whenever the voltage that is appearing across the anode and cathode of the diode is positive, then simply it can be represented by the closed switch. And as you can see over here, the applied voltage across the diode is 10 volt. So simply it can be represented by the closed switch. And the current that is flowing through this 100 ohm resistor will be equal to 10 volt divided by 100 ohm, that is equal to 0.1 ampere. While on the other end, if we apply the minus 10 volt in this circuit, then the applied voltage across the diode will be minus 10 volt and it will not allow any flow of current. So simply it will act as a open switch and the current that is flowing through the circuit will be equal to 0 ampere. Now some of you might have a question that how to find the voltage across this diode. So that can be found by finding the Thevenin's equivalent voltage between these two terminals. So simply you need to remove this diode from the circuit and you need to find the Thevenin's equivalent voltage between these two terminals. So if you remove this diode, then the Thevenin's equivalent voltage which appears between this anode and cathode in this particular case will be equal to minus 10 volt, and because of that the diode will be non-conducting. On the other end, whenever the 10 volt is appearing between these two terminals, then diode simply will act as a closed switch. Now if you see the VI characteristic of this ideal diode, then you can observe that even if we apply very small positive voltage between this anode and cathode, then also this diode will start conducting. So let us say even if we apply the positive 0.1 volt between this anode and cathode, then also this ideal diode should start conducting. But if you see the actual diode, it will start conducting only after the applied voltage cross some threshold voltage. And if you see the VI characteristic, then it will look like this. So up to certain threshold voltage, the diode will not allow any flow of current. And whenever the applied voltage crosses this threshold voltage, then only diode will allow the flow of current. So this voltage is known as the threshold voltage or the cut-in voltage for the diode. Now like I said before, this diode is a semiconductor device and usually it is made up of either silicon or germanium. So for silicon, this threshold voltage used to be in the range of 0.6 to 0.7 volt, while for germanium usually it is around 0.3 volt. So actually the diode will start conducting once the applied voltage crosses this threshold voltage, and before that it will not allow any flow of current. So this is the first approximation for the diode curve. So here in this approximation we are considering this diode as an ideal diode, but it will only allow the flow of current once the applied voltage crosses this threshold voltage, and the equivalent circuit will look like this. So in case of reverse bias, it will simply act as a open switch, but whenever the applied voltage crosses this threshold voltage, then only it will allow the flow of current and simply it will act as a closed switch. So now let us take the same example that we have taken earlier. So in this approximation we are considering this diode as an ideal diode, except the fact that it will allow the flow of current only after the applied voltage crosses the threshold voltage. And here we are assuming that the diode that is used is the silicon diode. So it has a threshold voltage of 0.7 volt. So once the applied voltage crosses this 0.7 volt barrier, then only it will allow the flow of current. Now here, as the applied voltage is 10 volt, so simply this diode will allow the flow of current, and the equivalent circuit will look like this. So now if you find the current that is flowing through this 100 ohm resistor, it will be equal to 10 volt minus 0.7 volt divided by 100 ohm, that is equal to 0.093 ampere. While on the earlier case, when we have considered this diode as an ideal diode, at that time we found the value of this current as a 0.1 ampere. So using this approximation, we can find the more accurate values of voltage and current in the circuit. Now in the same approximation, suppose if we apply the minus 10 volt, then in that case the circuit will simply act as a open switch and it will not allow any flow of current. So the current that is flowing through this resistor will be equal to 0 ampere. Now in this first approximation also, we have considered that the diode has a zero resistance, and that can be also visible from the VI characteristic of this diode, because if you observe over here, once the applied voltage crosses this threshold voltage, then the voltage that appears across the diode will remain constant and only current will increase. It means that the diode offers the zero resistance. But in actual case, every device has some finite resistance which will limit the current that is flowing through that particular device. So now let us consider the second approximation, where we are also considering that the diode has some finite resistance, and in that case, if you see the VI characteristic, then it will look like this. So up to the threshold voltage, the diode will offer infinite resistance, or simply it will act as a open switch, and then after it will provide some finite resistance, and that resistance can be found from the slope of this curve. So this resistance is also known as the bulk resistance or the body resistance. So this resistance is the resistance that is offered by the semiconductor device out of which this diode has been made. So now let us see the equivalent circuit for this second approximation. So whenever the diode is reverse biased, in that case simply it will offer the infinite resistance, or we can say that it will act as a open switch. But whenever the applied voltage crosses this threshold voltage, in that case now it will offer some finite resistance of RB, that is the bulk resistance of this diode. So this is the equivalent circuit in case of the second approximation. Now apart from this bulk resistance, diode has one more resistance, and this resistance is present in the diode because of its internal structure. So we will talk more about this diode resistance in the separate video. Now typically the value of this resistance used to be a few ohms. So in the circuit, if the Thevenin's equivalent resistance which appears across the diode is much more than the diode resistance, in that case the diode resistance can be neglected. But if the Thevenin's equivalent resistance which appears across the diode is comparable to the diode resistance, in that case we also need to consider this diode resistance. So for example, in this case, let us assume that the diode has a resistance of 25 ohm. Now this resistor is comparable to this 100 ohm resistor, so we need to consider this diode resistance. So if we consider this diode resistance, then the current that is flowing through this 100 ohm resistor will be equal to 10 volt minus 0.7 volt divided by 125 ohm, and if you see the current, it will be equal to 0.074 ampere. So because of this diode resistance, if you see, now the actual current that is flowing through this 100 ohm resistor will change. So using this second approximation, we can find the more accurate value of the current and voltage that is flowing through the circuit. But in most of the circuits, the Thevenin's equivalent resistance which appears across a diode used to be a much larger than this diode resistance, and simply we can neglect this diode resistance. So in this second approximation of this diode, we have assumed that the diode is non-conducting till the point the applied voltage crosses the threshold voltage, and then after it offers some finite resistance. So if you see this type of characteristic, then it is known as the piecewise linear characteristic, because what we have done, we have segmented the actual characteristic of this diode into the piecewise linear characteristic. So up to the threshold voltage, we have assumed that the diode is non-conducting, and after the threshold voltage it will offer some finite resistance. Okay, so now let us talk about the actual curve of this diode. So in this diode curve, like I said before, this region is known as the forward region, because once the applied voltage crosses the threshold voltage, then the diode starts conducting, and whenever the applied voltage is less than the threshold voltage, in that case the current that is flowing through the diode is almost negligible. Now whenever we apply the reverse voltage to this diode, then that region of operation is known as the reverse region of operation, and in this region the current that is flowing through the diode used to be a very small, typically in the microamperes, and this current is known as the reverse saturation current of the diode. So as you can see from the graph, even if we increase this reverse voltage across the diode, then also the current will only increase by marginal amount, but we cannot increase this reverse voltage indefinitely, because if we go beyond certain voltage, then the diode will come into the breakdown region. So this region of operation is known as the breakdown region, and this region of operation should be avoided. Now some diodes are specifically made to operate in this particular breakdown region, and this type of diodes are known as the Zener diode. So we will talk more about this Zener diode in the separate video, but for any normal signal diodes, this region of operation should be avoided. So if you see the data sheet, you will find that the maximum breakdown voltage for the diode has been mentioned. So the applied reverse voltage should be less than this breakdown voltage. Now in the forward region of this diode characteristic curve, if you observe, as the voltage across a diode increases, the current that is flowing through the diode will increase exponentially. So in data sheets you will also find one more parameter that is known as the maximum allowable forward current. So diode current should be less than this maximum allowable forward current. So here are the few parameters that we will find in the data sheet of any diode. So now in the next video we will talk more about the diode resistance. So I hope in this video you understood what is diode and the VI characteristic of the diode. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.